Welcome. Last video we looked at the first topic, that is vector and linear combinations. And today what we are going to do, we are going to solve few problems based on vector and their linear combination. Before starting, let's review what we have done in last lecture. After reviewing the last lecture, we are going to solve problems. So in last lecture, the first point, I talked about the vectors. So a vector v in two-dimensional space has two components, v1 and v2, right? Similarly, if I ask you give me a vector from three-dimensional space, then it will have the three component v1, v2 and v3. Similarly, if I ask you that give me a vector from four-dimensional space, then you will say that it will have the four component, right? Similarly, if I ask you give me a vector that belongs to n-dimensional space, then it will have the n component, because to specify a vector from n-dimensional space we need n component to specify that particular vector. And the second point, we looked at the two very main operations, that is the vector addition and the scalar multiplication with the vector. And we saw that these two operations are very important to define the linear combination. Not the important, but I can say these two operations combinedly defines the linear combinations of vector space, right? So we saw how to add two vector in general. What you have to do, add those vector component wise, and at the last also we looked at that we can write a column vector. Suppose you have the column vector written like this, and this is similar to, you can write with this comma separated, right? And this is not a row vector. We will look at row vector also, but do not get confused with the notations, all these things. So this is just a writing different way of this column vector, right? So similarly I have written like this. So uh, apart from this, what I am talking about right now is the operations, two operations, that is vector addition and the vector multiplication with a scalar, and these two operations can be done with component wise. And we looked at linear combination of vectors, right? We started with two vectors that are from the two-dimensional space, and we took two vectors from those dimensions and we looked at their linear combination. So a linear combination of three vector, if we look at the three vector, that is u, v and w, it, so that linear what will be the linear combination? That will be this, right? With these two operations, what we will do, we will simply scale the vector u, scale the vector v, scale the vector w, and we will add those, right? And this will what give us the linear combination of vector u, v and w. And also we looked at that, we talked about the spaces they are going to, you can say span, or let me not introduce this term span right now, or we looked at the spaces, right? What they are going to expand, right? The that linear combination may, so the point is that if we are taking the, let's suppose take all linear combination of u, you can take the linear combination of u, that is c times u, right? Or you can take the linear combination with u and v, that is c times u plus maybe w times v. So these c and v are the scalar and these two are vectors. Or what you can do, you can take the linear combination of c times u plus d times v plus e times w. These are the scalar one and these are the vectors, right? In 3 dimensions, those combinations typically fill a line. So if you are taking only one vector, then it is going to fill a line. C times u will, obviously that is going to fill a line, and we have looked all these things in very detailed manner, right? And if we have two vectors, then they are going to fill the plane, and if we have all three vectors, that is in different direction, and if we take the linear combination of those three vectors, then it is going to fill the, their linear combination is going to fill the whole space, that is rq. Now here you see that this notation may be new to you. Let me just tell more about this. So r is nothing but a real number. That is how we denote this. This is nothing but real number, or you can say this r is nothing but a real number from one dimensional space, right? And if we have r and in power we have 2, that is again you can say, instead of taking a number, now we are talking about a vector, and it will have the two component, right? Now we will have space that will be two dimensional space, right? So this r square is nothing, but you can say that r belongs to some real number, and so the vector we will have the component here, those will be real number, and this 2 is nothing but the, it is specifying the space from which space these vectors are coming, right? Similarly we will have rq, that means we will have real vector with three component, and it will again have the three dimensional space. It has came from the three dimensional space, and analogous to that we will have the n dimensional space, right? Okay, now we are done with the review. Now we will be jumping with the problem that we have discussed in last lecture. Okay, now let's start with the few problems. So let's look at this first problem. So the problem is the linear combination of v. So we have given this vector v, and if you see it has the three components, that means it, this vector belongs to some three dimensional space, and we have another vector that is w, and again it has three component, that means this w will also belongs to some three dimensional space. So we have given the information about v and w, that v and w fill a plane in three dimensional space. So what does it mean by rq? We have the three dimensional space, and in this three dimensional space v and w, their linear combination is filling a plane, right? So you can think of it, if you have three dimensional space, there is a plane, right? There is a plane with the linear combination of v and w, right? So these two vectors in three dimensional space are filling a plane, right? Not the complete dimension, not the complete 3D space, but just a plane, right? Describe that plane. So we have already seen during our lecture, and one more point, it is asking that find the vector that is not a combination of v and w, or you can say that that is not on the plane, right? That is not on the plane, or you can say find that vector that is not a combination of v and w. Okay, let me first of all find the linear combination of v and w. So if I am asking you about the linear combination of v and w, what you will give me? You will simply multiply the scalar quantity with v and multiply the scalar quantity with some d with vector w, and you will add those two and you will give it to me, and you will say that the linear combination of v and w is this one. right? So we can write this as c times we have vector v, that is 1 1 0, and d times we have vector d, that is 0 1 1. And we have seen that how to add or how to do the scalar multiplication. So you can carry out, so that will be c plus d and d, right? So this is the linear combination of vector v and w. And this vector, so you can take any value of c and d, and their linear combination of v and w is, you can take any value of c and d, right? And the linear combination of v and w is going to fill up a plane in three-dimensional space, right? And if you look, so in theory we have already discussed on this, but let me just give you a picture that how it will look like. So let's suppose that we have this space that is three-dimensional space, and let's suppose this x, this is y, and this is z, right? So v will be somewhere in 1 1 0. So we, let's suppose that this is a vector v in xy, and let's suppose this is a vector w, that is maybe this one, this is a vector w, right? So you see this is let me also, this is a three-dimensional space if you are able to visualize it. And so in this you will have the plane, let me draw that. So maybe the plane will look like something like this. So this is not, it will be a so this vector w can go in opposite direction also, right? And this, so the plane will look like something, so it will be, right? So this plane will pass through the origin, and this is how it will look like. So okay, now find the vector that is not a combination of v and w, right? So let me first of all give you some vector that is the combination of v and w. So we can have 1 2 and this is 3, because so this vector will belong to, this vector will be on the plane of the v and w, or you can say this vector will belong to the linear combination of v and w. How? You see that you can pick any value of c, you can pick any value of d. So the vector you will get will have the component c and d, and the middle component will be the sum of c and d. So you can pick c as 1, d as 2, right? And you see that this middle component is nothing but c plus d. So this vector will belong to on this plane, right? On this plane means the linear combination of v and w. So this will be a specific choice of c and d that will give you a particular linear combination of this v and w, right? Similarly, we could have also a vector with pi and 2 pi, right? So this is c and d, and this is c plus d, right? So this vector will also belong to the same plane, or you can say this vector will also belong to the linear combination of v and w, right? And find the vector that is not a combination of v and w. So we can take many vectors that will be not in the plane, or that will be not the combination of v and w. So let me also, you see that 0 0 0 is also this vector will also belong to this plane where we are taking the linear combination of v and w, right? Because if you take the c and d is 0, and sum of these two will be c plus d, that is 0. So this vector will also be on the linear combination of this v and w, right? And you can take any vector that is not satisfying this condition with c and d. So 1 2 3, right? So this will be not the combination of, not a combination of v and w, right? Or you can say not on the plane, or not on the plane of the linear combination of v and w, right? So okay, now we will look more question. Let's look at second question. So this is question number 2. We have given this vector v and this vector w, and if you see, it has two components, w has also two components. Describe all points cv, and here we have given the information about that of c, what value of c we can take. And with, so in first we have to take the whole number c. So whole numbers are nothing but starting from 0 1 2 3 4 and so on. So this is a whole number. So c cannot take, c can take only these numbers 0 1 2 3 4, all the positive integers including 0, right? And it is not going to take any kind of fraction, it is not going to take any kind of decimals number, right? And the second, so let's look at the first one first of all. So we have given this two vector, right? That is vector v and u. So we can write vector v 1 0, and we have given this vector w, that is 0 1. If we have to represent this pictorially, then we can do that, right? So this is going to be vector v with 1 0, and this will be vector, or first let's look at the first one. So describe all the points cv. What will be the cv? So what we are doing, we are only doing the scalar multiplication with this vector v. So cv will be c times v, that is c times 1 0, and that will be c 0, right? So this c 0, and what value of c we can take? C we can take 0 1 2 3. So what is the space you are going to get with this combination of v, right? So you will have the vectors, that is 0 0 1 0 2 0, right? So and so on. So you will get so we have to describe all the points, right? So the points you will get is 0 0, this one, right? And 1 0 and 2 0 and so on, right? Now let's look at this. So this is the first part, and the second part we have that c is greater than 0. here if you see, c is non-negative, c is greater than 0. So c can take any value that is greater than 0. C is greater than equals to 0. It can take integer, decimal, everything, right? That is greater than 0. So if you look at this, so we have this v vector here, right? So now c can take any value that is greater than 0. So what you will get is a line along the vector v, right? So in first case what we are getting is the point, right? Because why we are getting the point? Because we cannot, with this definition of c, we cannot reach to these sections. We cannot reach to these sections, right? But we can reach to these with the red dot section, right? So with this c, we will not have these pink one, right? With this definition of c, where c is whole number, right? So the space with this combination we are getting is the point only, and that point is even on, you can say, on the x-axis or along the v vector v, right? But what happens in this case where c is greater than 0? So we can reach to any point that is greater than 0 and that is along this vector v. So you can reach to here, you can reach here, you can reach here, you can reach here, you can reach any point with this particular definition of c, right? So in this case what you are getting is the line along the you can say along the vector v or positive x-axis. Okay, now we have a few more question on this, and what it is asking that then add all vector dw and describe all cv plus dw. So again we will be taking these two cases of c where c is whole number and c is greater than equals to 0, and we will see that what kind of space this combination is describing, right? So let's say call this one dash. Here again c is whole number, so c is whole number and it can take only this value, integer with including 0. And also now we have this dw, right? And we have nothing said about this d. So what I am assuming about the d is a real number, and what combination we have to look is that cv plus dw, right? So let me draw. Right, so c d is any real number, right? First of all write the so c times v is 1 0 and plus d is w is 0 1 here, right? We have given this in the question. So 0 1. So if I have to draw this v and this w, then I can draw it, right? We have seen the way of drawing the vectors, right? So this will be your vector v in this direction, and this will be your vector w in this direction, right? So what will be the complete space with this particular choice of c and d? right, that we have to answer. So how we can look, let's pick a specific value or specific value of c and d. Let me pick c and d as 0, so obviously that is going to be 0. Let's pick c, we cannot pick any fraction or a decimal value. We can take, let's take c is equals to 1, and so this d could be any real number, right? So let's pick d also as 1, right? So with this what we will be getting is uh, 1 0 plus 0 1. So the point we will be getting is 1 1, right? So we will have this point that is 1 1 somewhere here. Let, you can do one more thing. Let c to be fixed, let's or let c to be fixed, and let's vary the value of d, right? So we can pick d is equals to from plus infinity to minus infinity, right? Because d is a real number, right? So we have picked a specific value of d, but what we are going to do, let's vary this d, right? So now I want to see that what space I am going to get, right? So c is 1 0. With this value we will be here, and now from here if we vary this value d from plus infinity to from minus infinity to plus infinity, then we will have this line, right? And why cannot have this line between 0 and 1? Then that will be not getting satisfied with the value of c, right? So that is the one thing. And is this the complete space? No, we could have more. We can pick c is equals to 0, and again we can vary this d, right? So we will, with particular value of c is equals to d 0, here we will have, and if we vary d now, that will be along the vector w again, and this is the line that you will get, right? So this is the line you will get, this, and none of the thing that you are going to get in between these two. Think about it, why we are not going to get a line that is in between these two at any places. These are not these lines, you are not going to get it. Okay. With this similarly we can get a line that will be passing through this point 2 comma 0, and we will have this line. So how I can describe the space with this particular with this particular combination of c and d? The space of this vector v and w, or you can say something like this, the the space of the linear combination of this v and w with a specific choice of c and d, what you are going to get is a line that will be parallel to this vector w, and all these line will be in the positive uh, positive half plane, right, in this direction, right? You cannot have the line that will be in this direction. Okay, I think you have got the idea. Now let's look at this 2 dash case. So we have, so now we have here c c is greater than 0, right? So and c can take these all the value that is greater than 0. It could be a decimal, it could be a fraction, it could be any number that is greater than 0, right? And d is again here real number. And what we want to see is the with this space, with this particular value of c and d, what we want to see is the what space we will have when we will take the linear combination of this vector v and w. So let's take the linear combination of this vector v and w. So can you visualize what kind of space you are going to get with this value c is greater than 0 and d could be any real number? Can you answer this question? So let me describe this one also. We will have more question on this where you will have to answer what is the space you are going to get when we are taking the linear combination, or what is what space will what space will be described by the linear combination. So this kind of question you will get more. Okay, now we have our vector v in this direction and we have our vector w that is in this direction, right? And so what is the space that will be described by this linear combination? So c is greater than 0. So let me how I can think about this. What I will do, I will simply set d is equals to 0. I will simply set d is equals to 0 and I will let vary c. So vary c. So now I will visualize this. If I am varying c and letting d is equals to 0 and c could be value that is greater than 0, so I will be getting this kind of space, right? So and if I and what more I can do, I can set c is equals to 0 and vary d. If I do that, what I will get, if I set c is equals to 0 and vary this d, then I will be getting this, right, along the vector w, right? And now think both. So you can take any value of c, so c could be here also, and for all value of c you will have the w, right? So the space that is going to be spanned by this, or the space that with the linear combination of this you will get, is the complete half plane, this complete entire half plane, right? Because now you see in this case we have this gap remaining, right? Now since we can take any value of c, now we will not have these gaps, we will be filling all this, right? There will be no gap. So what you will get is the complete half plane. So you will have this. So that is going to be till infinity. So in this case you will get the half plane, and here you will have the parallel lines. Okay, let's look more problems. Let's look at this question number 3. So we have find two equations for c and d so that linear combination cv plus dw equals to b. So you see we have given this two vector here, right, v and w, and we have to find a particular or a specific, a single combination. I mean to say that you have to find a single value of c and d such a way that that with that particular value of c and d you will be getting this vector, right? So so far you have also seen that we have, if we have two vector, right, these two vector, using these two vector, if you take the linear combination, you can reach to any point in two-dimensional space if these two vectors belongs to two-dimensional space, right? So that is what we have been asked, that for what value of c and d, with, if you take the linear combination of v and w, for what value of c and d you will get this point, right? So this is how you can think of this. And so if you take the linear combination of v and w, so how we can take, we can, so this is the linear combination of v and w, so this should give you what, this should give you b, right? So what value of c and d you will take that will produce this b. So we have been asked that what is c and what is d. So proceed as usual. What you can do, you have c and v, that is 2 minus 1, and plus d is not known to us, w is minus 1 and 2, and what we want is 1 0. So for what value of c and d, we can write this as 2c, scalar multiplication, remember, and plus we will have here minus d, right, and here we will have minus c plus 2d, this should give 2 1, and this component should be 0, right? So what we have done is simply we have performed two operations, that is scalar multiplication and the addition, right? And the first component should be 1 and the second component should be 0. Now we have these two equations, right? We can solve these two equations and we can get the value of c and d. So what we can do, we can multiply this second equation by 2, or you can multiply the first equation by 2, so you will have 2d is equals to 2, and in the second equation is, so this here we will have minus, right, and the second equation is this will get cancelled, and here we will have 3c is equals to 2, so c is equals to 2 divided by 3, and you can put this value of c in any of equation. So let me put it in second equation, so 2 divided by 3 plus 2 times t is equals to 0, so d will be 1 divided by 3. So you have got your, so our question was for what value of c and d you will get this b, right? Now you can check by putting here c is equals to 2 by 3 and d is equals to 1 by 3, then if you do the calculation you will get this one. Okay, now here I want to talk more with this equation. And first of all, so in further videos, that is our the second chapter, where we will be solving linear equations, right? And if you see here we have two equations and two unknown, right? And in second chapter we will have the 1000 equation, and we will be solving with so these that with the 1000 equation, this procedure is not going to work for us, right? That we have done. So we will, so it's a kind of elimination, right? So we will look more on the second chapter. Let's not talk about as of now. And one more point, since we are going to uh, in third, so we are going to talk about the matrices. So we have this equation, right? So we can write this equation as a matrix form. So let me just write it down. We will talk more about matrices in upcoming videos. So if we have this linear equation, then we can write these equations as a matrix equation. So what we can do, we can simply put these vectors, that is v and w, as a column of matrix. So this is vector v, and the second column is vector w, and the and we can multiply with this our c and d. So this is nothing but, this multiplication is nothing but what you are doing is taking the linear combination of this vector, these vector, and with this unknown. So let's not talk about this as of now. Let's write this the matrix equation. So this is what I wanted to tell you about this matrix equation. So this is a matrix equation, right? And we can, this is a matrix, and let's call this matrix A, right? And this is our unknown, let's call this X, and this is what we want to get. So Ax is equals to B as a matrix equation. So we will talk more about on matrix equation in upcoming videos. Okay. Okay, now let's, so these are the problem that you need to solve, right? So you can go through each problem and you can try to solve. So we have these problems. So I would recommend that you should definitely try problem from the question number from 1 to 5, right? And if you are able to do that, this problem, that means you have got the idea behind this linear combination, right? So it's recommended to solve these questions from 1 to 5, and if you think that you can easily solve this question from 1 to 5, then you can go on with this question number 6, right? So these are the problems that you need to solve from your side. Okay, so and if you have doubt in any problem, you can comment it. I will go and look those comments, and in next video, first I will solve those problems which you have faced the difficulties while solving, right? And yeah, also okay, let's see how we are going to go, or how we are going to coordinate with this section, with this homework problems. So this is the first time, right? So let's look at, so I would say that solve these problems. If you have uh, difficulties in solving these problems, you can also write me a email that uh, I am not able to solve, or I am not able to understand this problem. Then we will find the solution for that one. And if you have understood the concept, and if you are able to solve this question, attempt these questions. And if you have any doubt in in some questions, then you can comment uh, those question number. And what I will do, I will check the comment, and I will go through those questions, and I will try to solve your doubt in next video. Okay, and maximum what I will be doing at the end, I will go through each problem, uh, whatever the homework you have assigned, I will go through all of those problems. Yeah, that is all from all this video. Once we are done with this homework problem, we will be jump to our second topic, that is the length and the dot product. This one, right? We will not spend too much time on this topic, and then we will jump to this third topic, and we will end up with this our first topic, that is introduction to vector. Then we will jump to solving linear equation. Okay, that is all about this video. Thank you.